Hi, this is Chris, and we're taking a look at our next couple parts of our bungee jumping situation here for this physics question. So again, we're dealing with free-falling bodies, we're dealing with springs, a lot going on. And if you haven't gotten caught up to this point, check out the earlier videos. But basically, we have a bungee jump apparatus for adults, and someone's jumping and they give us the lengths of these elastic cords that are tied to the ankles of the jumper, and they're going down, 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 down until they reach the full length of the cords, and then the cords start stretching. So they stretch a little bit. We're dealing with spring force at that point, and they stretch all the way down to the bottom part of the jump, and then it starts pulling them back up. So just like you could envision a bungee jump, that's what they're describing here. And we are on to part D, where it says, is the jumper's momentum changing at this instant or not? And the instant they're talking about is what they mentioned in one of the earlier questions. They're talking about this instant where there's the greatest tension in the cords, which is when you're at the bottom. That's when those bungee cords are fully stretched and they are going to be pulling with the strongest force to pull that bungee jumper back up. So that's the instant that they are referring to. The speed at that instant, as we said in C, is 0 because we reach the bottom of our jump. So for that brief moment, we pause and then get pulled back up. And they want to know about momentum change. And I want to highlight that. They're not asking what is the momentum, because the momentum would be 0 at that point. Momentum is going to be your mass times your velocity. And if your speed is 0, if your velocity is 0, then your momentum would be 0. But that doesn't mean it's not changing. And what we see happening here is that we're moving down at some velocity, and then we slow down, slow down, slow down, slow down, slow down, stop, and then start speeding up, speeding up, speeding up, speeding up, going back up, the other direction. It doesn't look like a U shape because it's not a projectile. It's going to be just straight down and then straight back up. But I wanted to draw that out so that we can reference the momentum change. Here, our velocity is in the downward direction, and then our velocity is going to be pulled back up in the upward direction. And our acceleration, this entire route, let me color code this a little bit. But even though our velocity is still going down, as we come to that stop, as we come to a halt, our acceleration is pulling up the entire time. We are experiencing a net force the entire time. That extended bungee cord is pulling us back towards equilibrium. So we go down, 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 down towards this point. But our momentum is changing because our change in velocity, the velocity might be going down, but the change in velocity is going to be the same direction as acceleration. Change in velocity is going up, change in velocity is going up, change in velocity is going up. We still have a magnitude value for the change in velocity. So yes, when we're asked this question about change in momentum, the momentum is changing. Even at the split second where it happens to be 0, if you go from positive 4 and then eventually you go towards negative 4, even if you reach 0, somewhere in between those values, there's still going to be a change that's taking place. If you go from negative 12 and then you end up at positive 3, right? Somewhere in between, you might hit 0, but it doesn't mean that no change is taking place. It doesn't mean that it's static when you get there. Just because you cross a 0 point does not mean that there's a lack of change. So be very careful with the way that questions are worded. But when they talk about change in momentum, momentum is changing as velocity changes. And even a change in direction for velocity is still a change in velocity. It doesn't even have to be a change in terms of magnitude. So that's a really important concept. And it's a great question that they ask because it is a really good take-home concept to make sure that we understand about this type of scenario. All right, now let's take a look at part E. It says, which of the following statements is a valid basis for answering part D correctly? A very short time ago, the momentum was downward and non-zero. Okay, I think that's fair because, yes, at this point, We said that it was downward, and we had an actual value for velocity and obviously for mass. The person doesn't dissipate into the air along the bungee jump, so the mass is still going to be there regardless. But yes, we do have a non-zero value of velocity, and so if we get to this bottom portion of our jump where velocity is 0 for that moment, well then if you had a non-zero value that goes to 0, there has to be some sort of change. So I think that's a fair box to check for what indicates that we do in fact have a change in momentum. Let's check the next one. It says since the net force must be 0 when the momentum is 0, and since dp in the y direction, dt, is equal to the net force, dpy dt, must be 0. Well, they switch the wording up on us here because they're talking about momentum being 0, but then they're concluding that dpy dt is 0, and that's change. And as we mentioned in here, just because you reach a 0 point does not mean that there's no change taking place. So that is actually a very different conceptual idea of having a momentum of 0 and having a change in momentum of 0. That one is not going to be true. So when you talk about net force, you're talking about a value of acceleration, and just because velocity hits a 0 point somewhere along the path does not mean that the acceleration has to be 0. Just like if you were driving a car and you slammed on the brakes, as soon as you come to a stop, right, your acceleration is still opposing the direction of motion. So you can still have a deceleration taking place, or a value of acceleration in the opposite direction. It doesn't have to mean that your net force is 0 at that moment. So that one we're definitely not going to check off. Let's take a look at the third one. After a very short time, the momentum will be upward and non-zero. And this is kind of the same thing as that first one. A short time ago, it's downward and non-zero, and then a short time after, it will be upward and non-zero. So we get to that little stopping point, pause briefly, and then go back up. So that is also indicative of a change in momentum. If we went from a 0 value to a non-zero value, we're going to have a change in momentum. Let's take a look at these last two. If the momentum weren't changing, the momentum would remain 0 forever. I don't love the wording of this, but yes. So at that point, because again, we are talking about technically, just for part D, it's at this instant, right? And when they say this instant, you are talking about at the very bottom of your bungee jump. So right as you get to that bottom point that we see here, so at that instant, at that moment, if the momentum is not changing, then you have a 0 momentum. So if there's no change, it would technically remain 0 forever. So we can say yes to that, although that wording is not very specific to provide a little clarity to the situation. But yes, if you are at that instant and the momentum is 0, then 0 change would mean that you would remain at 0 forever. And the last one, since the momentum is 0, the momentum isn't changing. I think we've discussed that, but no, just because you have a 0 point does not mean that there's no change taking place. You could be in between switching from a positive to a negative value. You could be changing different kinds of magnitudes. You could be changing direction. So no, a momentum of 0 at one moment does not mean that you're going to have a lack of change in momentum across the board. So it's just going to be the first, third, and fourth of these tenets here that provide a valid basis for the answers for part D. Up next, we're going to take a look at some of the calculations that we see here in FH.